So, here's what we're going to do. JC, I don't know why you're wandering around, but, we could just sit down and wait for instruction on those. Yeah, we can just wander around freely. It's a nomad. It's a nomad classroom. We learn better as we roam around like a nomad. Half-angle identities, we're just going to look at them, we're going to apply them right away. We're not going to prove them or derive them. There's a small derivation here for the cosine one. All the others are identical to it. But what we're going to focus on is how can we use half-angle identities to help us find the exact values of other angles that we don't know the exact values of. So here they are. There's a lot of similarities between the two identities for a sine of a half angle and the cosine of a half angle. All we got to do is switch the signs. Just like our power reducing, these are identical except for the plus and the minus. And then we got a tangent. Well, the tangent's confusing because it has three versions, three forms of whichever one we want to use. So again, strategically picking the one that's probably the easiest for to use would be one of your main decisions. So we're going to take these and we're going to use them in two examples just to show you how we can apply them to find exact values of angles we wouldn't know the exact values of by using them. So, question 5a, find the exact value of each expression, the sine of 75 degrees. The first issue I want to raise is 75 degrees, one of those 30, 60, 90, or combinations of 30, 60, 45, 90. No, can't build it out of 30s, can't build it out of 45s. We could do 30 and 45, we could do a sum, and we've seen us doing that. But they want us to use the half angle identity. So evidently, 75 is half of an angle we would know. So we just simply take that angle and double it. So I'm going to rewrite the sine of 75 as the sine of 150 divided by 2. Is this still 75 degrees? Yes, it is. That's the idea behind it. We're going to be able to find the exact value of 75 by being able to take half of a 150. So we're going to apply our half angle identity for sine. Okay, so I'm sneaking up there and I'm looking at that. Here's the one we want. It's the square root. Oh, look at that sneaky bugger. Plus or minus. So plus or minus the square root of this whole thing, which is 1 minus the cosine of theta divided by 2. So this is what we're going to apply. If you look at your formula, it says the sine of theta divided by 2 equals, then plus or minus. The part I want to emphasize is 1 minus the cosine of theta. What is theta in this problem here? 150. It's this 150 that is theta. So we're going to come and we're going to plug in plus or minus the square root of 1 minus the cosine of 150 all over 2. I didn't make a big issue of it, but why is 150 a decent angle? It's a multiple of what? 30. So we know a 30, so we'll know a 150. Another issue you should resolve probably immediately. A 75-degree angle is what quadrant angle? It's a first quadrant angle. The signs in the first quadrant, are they positive or negative? So you get to pick right off the bat, it's going to be a positive. You don't have to worry about the negative. It isn't both plus and minus. It's one or the other, and you have to choose. You always choose by where was your original angle. That was in the first quadrant, so it'll be plus. Okay, so now we have to calculate the positive square root of 1 minus the cosine of a 150. So I'm going to do a reference triangle for a 150-degree angle. Here's 150 degrees of angle rotation. Our reference angle then is a 30 degree. If it's a 30 degree reference angle, then what are the measurements on our triangle? 1, 2, square root of 3. They want us to find the cosine of a 150 degree angle. Very close. Yep, you have to include the sine. Cosines are to the left of the origin in the second quadrant, so it's negative, all over 2. Now it's a matter of some algebra and simplifying. A double negative really is a positive. So minus negative is just 1 plus the square root of 3 over 2, all over 2. Yesterday we had to simplify one of these complex fractions. In order to get rid of this division by 2, we said we want to take the top and the bottom and multiply it times 2. So it equals the square root of 2 plus square root of 3 all over 4. And keep in mind, this radical goes all the way down. I want to remind you of a radical rule that says if you have the square root of a divided by b, the square root of a quotient is the quotient of the square roots. So really what I could do is write this as the square root of 2 plus the square root of 3 over the square root of 4. And that has a strategic advantage. The square root of 4 is 2. So our final answer is the square root of 2 plus the square root of 3 all over 2. This is the exact value, and that's what we were after, not a decimal approximation, but the exact value of the sine of a 75. Now, we could use our sine of a sum identity on this too. It's just that they were descriptive in saying, use your half angle identity. And we did this same problem earlier as a sine of a 30 plus 45 degree. And then we use the sine of a sum identity. It will give you the same answer. In line? Okay, so let's go to a radian measure. Radian measures aren't any more difficult. What did we do to get our half angle identity when it was 75? So we took the sine of what? 150. We simply took that and doubled it. So we should take this and double it. We want to find the tangent of what is double 7 pi 12. So yeah, we take it times 2. It gives us 14 pi 12, which is equivalent to
300.
wow, 7 pi 6. You're not going to convert it into degrees. It's just 7 pi 6. Now, is half of 7 pi 6 equivalent to 7 pi 12s?
No. Oh yeah. Yeah.
You'd have to multiply by the reciprocal, so that's 7 pi over 6 times 1 over 2. This is equivalent. So we're going to use our tangent of a half angle identity. So sneak up here and find it. We've got 3 choices. It really shouldn't matter which choice you choose. I'm going to choose the top one because I can just work with cosine of theta, cosine of theta. If you don't like radicals, are those more appealing without radicals?
Yeah.
All right, so let's look at one without radicals. Second or third choice?
Third
Choice, it's sine of theta over 1. So sine of theta over 1 plus, it was a cosine of theta, wasn't it?
Yeah.
Just making sure.
Cosine of theta.
Okay. So we got to plug in for theta, what angle? 7 pi 6 over 1 plus the cosine of 7 pi 6. We better get a look at this reference angle. Where does 7 pi 6 place us? In what quadrant? Third quadrant. So I got to wrap around here to the third quadrant, and our reference angle is pi 6. And you can say it's 30, but pi 6 is 30. What's always opposite your 30? 1. There's your 2. Square root of 3. So we need the sine of this. Well, since we're both left and down, it's negative and negative, so the sine is
1 over square root of 3. But it's both, they're both.
Sine is opposite over hypotenuse. It is y over r.
Negative 1 over.
Negative 1/2 over 1 plus the cosine of this.
Negative square root of 3 over 2.
Negative square root of 3 over 2. Okay, so we got to clear some fractions here. What would be a decent thing to multiply top and bottom by?
Multiply times 1 minus 2 over 2.
How about multiply by 2? Let's clear some of those fractions. If I multiply by 2, this becomes just a negative 1 over 2 minus square root of 3.
Then you can multiply.
Now we'll worry about rationalizing the denominator. We can't leave radicals, the square root of 3 in the denominator, so we'll multiply it times, what did we learn?
2 plus square root of 3.
2 plus the square root of 3. You multiply by its, what's the C word?
Cofunction. Compatible.
Conjugate.
Oh,
So when you multiply conjugates together, like these in the bottom, the outside insides cancel, so you'll be left with 4 minus 3 over, run your negative through, negative 2 minus the square root of 3. Or it's just negative 2 minus the square root of 3 over a 1, which is,
Negative 2.
You don't have to have that one, do
you do not. Okay, so now you've seen one example of it in degrees, one example in radians using half angle identities. I think that was a pretty wise choice of choosing the bottom one here. Either one of those would have worked fine. You see how maybe putting this second one would have been even better?
Oh, because then,
Maybe it would have been easier to rationalize the denominator. They should all lead you to the same ending place, but we chose this one in second period, and then we had to get clear radicals,
you?
which is a little bit more difficult. So choosing wisely helps. Okay, so just like all the others, after you learn how to use it, they want you to use them in solving equations. So solve each equation on the interval from 0 to 2 pi. Yeah, here we go. We got 2 sine squared of x over 2 plus cosine of x equals 1 plus sine of x. So what do you see in here that we just learned and should apply?
so if it's sine
This
squared,
part right here is your what?
you're half.
So we got a half angle identity inside of a
Square
Full
root.
angle identity.
squared. Do we have something that links back to that squared identity? Okay, so we're going to apply a half angle identity, and then we're going to square it. So here's our half angle identity. It's 2 times the sine of a half angle identity is what? Minus the cosine of x over 2. Now that's the cosine of our half angle identity, and what do we need to do with this answer? Square it. Okay, we applied a half angle identity, and then we were supposed to square it. Now it's going to be plus the cosine of x equals 1 plus sine of x. So when you square it, what happens to that plus or minus concept out there? Gets rid of it, because it's going to come back what kind of number? So it's going to be 2 times. Now what happens when we square the square root? So it's going to be 1 minus the cosine of x over 2 plus the cosine of x equals 1 plus sine of x. So what we're saying is when we square, it will undo the square root. And because squaring takes it, whether it's a positive or negative, it makes it positive. So it's 2 times this value here. But what do the 2's do? They cancel and they reduce. So it's 2 divided by 2. 1 is 1 minus the cosine of x plus the cosine of x equals 1 plus sine of x. Now we can reduce our cancels, or our cosine. So 1 equals, oh my goodness, we can cancel those two.
Sine of x equals 0.
So 0 equals the sine of x. So that means we have to be looking for every angle whose sine value is
0.
0.
Pi.
Which means y has to equal 0. And why is there only 0 at 0, pi, no, 3
Pi.
They got a square bracket on that one, so 2 pi. Solution set. So it's going to look complicated to start off, but you notice a lot of things simplified pretty quickly. Just got to check our time here. 21. We should be able to get this last example in. Okay, 8 tangent of x halves plus 8 cosine of tangent of x halves equals 1.
You're half right there.
So you see your tangent of half angle identity sitting in there?
You have 2 of them?
Yeah, we got a couple of them in there, so.
Let's use the same one for both.
Yeah, let's do plus the sine over 1 plus cosine.
Do you see how it's in each factor, though?
So what are you saying? Oh, you can factor it out.
That's what I'm getting at. We could get it down to tangent of x over 2 times,
8 plus. Oh, you can factor in 8 too, couldn't you?
if you want,
So 1
One
plus
time or the other.
cosine of x.
1 plus cosine of x equals 1. Now, typically, it's not the rule. It's more of the exception to the rule. We don't factor until after we have gotten one side equal to 0, but in some exceptions, this works a little bit smoother. So, tangent of x over 2. Let's apply that.
Sine
One.
Sine of x over 1 plus cosine of x.
So remember, we have 3 choices, don't we? And I already got a cosine there. So I made this choice. I said I made
no,
a
yeah.
1 minus the cosine of x over the sine of x. That's the one I used. We have to take that times 1 plus the cosine of x equals 1.
So, you should make it multiply the second one times sin x. Oh, no, you don't have to do that. 'Cause it's multiplication. Yeah, my bad, Alex.
So we're going to multiply straight across. So it's going to be 8 times. These two multiplied together give you 1
Minus cosine squared.
cosine squared of x all over a sine of x equals a 1.
Oh, that's the sine of x. Sine's canceled.
This is a sine squared of x, so
It's just sine.
Sine.
it's 8 sine of x equals a 1 because we can get rid of one of those powers.
Divide by 8.
1 over 8.
So sine of x equals 1 over 8, which means x is equal to the angle whose sine value is 1 over 8. And we don't know that.
I do.
So we are forced to pull out some technology on this one to figure out what those angles are.
Oh, you like something?
I don't really care to update. So we're going to run an inverse sine. This is something new. We haven't done this hardly at all.
Oh, man.
1 divided by 8, and I'm not sure what units I have it in. I'm going to go mode. We'll stay in degree. What angle is it? It says it's about a 7.18, so we'll round to the 10th. This angle is about 7.2 degrees. Now we got to be thinking, is that all of the angles in one rotation?
No.
Or is there another place where sines are positive?
Yes, in the second quadrant.
So in the second quadrant, we should have another angle just like this. So
Seven.
here is our one angle here at 7.2. The reference angle has to remain 7.2. So what is this measure?
80 minus 7.2.
180 minus 7.2. 172.8. Is that the only two locations where it is positive? Then we found our solution set.
Wow.
So what are we using? What kind of identities are we applying now?
Half angle.
Half angle identities. Enjoy the ride.